Hi, hello everyone. Today we are going to see about open mapping theorem. So the statement is B and B dash are the Banach spaces, and if there is a continuous linear transformation of B onto B dash, so it is a continuous linear transformation of B onto B dash, then we have to show that T is an open mapping. So it is a continuous transformation is we have to show that T is an open mapping. So for that, let T is a transformation, B to B dash is a continuous linear transformation. We have to prove that T is an open mapping. Okay, for this we have taken up an open set. So we have to prove that here B is an Banach spaces, B dash are the Banach spaces. We have to, for this we have to take up any open set G in B. We have to take a open set G in B, and we have to show that the direct image under operation T, under the transformation T, that is here under the transformation T, here it has a T of G. So T of G will be a open set in B dash. Okay, for we have to take B and B dash is a continuous linear transformation, and we have to prove that T is an open mapping. For that open mapping we have to take an open set in B, and we have to show that under the transformation T of G is a open set in B dash. By definition, T of G will be an open set in, which means by definition T of G will be a open set in B dash, and if about each point Y belongs to, if there exists a point Y belongs to T of G, then there is an open sphere which is contained in T of G. So there is an open sphere which is contained in T of G. If there exists a T of G will be an open set in B if about each point Y belongs to T of G, there exists an open sphere which is contained in T of G. Okay, now we have to take that Y belongs to T of G such that there exists, if Y belongs to, there has an image, mean it has a value that x in G. So for Y belongs to T of G implies there exists x in G, which means under the transformation of x such that T of x equal to y, because we have y T of G, there exists x in G such that T of x equal to y. So now x belongs to G, G is an open. By the definition there exists an open sphere. There is a element, and the element is contained in the open set, and there is an open sphere. Okay, by definition there exists an open sphere, says that is S of x comma r. Okay, x is surrounded by S of x comma r, that is contained in G, that G is contained in the Banach space. Okay, then we say that G is a open. By definition there exists a open sphere, say S of x comma r centered at x of the radius, it is center and radius is r, which is contained in G. Okay, this can be written as S of x comma r contained in G. This can be splitted into S of x comma r. By lemma we know that we can separate x plus SR, where SR is a open sphere of radius r centered at origin in B. So let SR be the open sphere centered at origin. So it is a open sphere centered at origin in B, so that T of SR is the image of an open sphere centered at origin in B dash. That is, for example, we can split this as x plus SR. Okay, where SR is a open sphere of radius r centered at origin of B. Okay, let SR be the open sphere centered at origin B, so that T of SR is the image of the open sphere. T of SR is the image of the open sphere. By lemma, we know that B and B dash are the Banach spaces. T is the continuous linear transformation of B onto B dash. Then the image of the open sphere centered at origin in B contains an open sphere centered at origin in B dash. So it contains an open sphere S R dash. By difference S R dash centered at origin in B dash. Okay, by lemma we have open sphere centered at origin in B dash. So T of SR open sphere centered at origin in B dash contained in T of SR. It is contained in T of SR, which means SR T of SR is SR dash. Similarly, so SR dash, the SR is centered at origin. Centered at origin, this is known as SR dash, but we have to prove that open space centered at origin in B dash is contained in T of SR. Okay, origin, that B dash, it is a B dash. The open sphere centered at origin here. Why? Centered at origin is known as T of SR. Okay, is contained. So SR dash is contained in T of SR. We have to prove that SR dash is contained in, because both are same. There exists an open sphere centered at origin. By lemma we having shown that T SR dash, but obviously we know that if SR is centered at origin, mean under the transformation it will be T of SR. What we have to prove means that SR dash is contained in T of SR. Okay, SR dash can be written as, that is SR dash can be written as taking y plus SR, taking both side add y plus SR dash contained in y plus T of SR. So y can be written as T of X, obviously it is T of X plus T of SR, and taking the transformation out means X plus SR. X plus SR can be written as S of X comma R. So S of X comma R is presented in G, so transformation of G. So this can be written as, if S plus X plus SR is written in the form of S of X comma R. So here is given as y plus SR dash. It can be written as S. It can be written as S of y comma R dash. So S of y comma R dash is contained in T of G. Okay, T of G. Hence T is an open mapping. We have proven that T of G. What we have to prove means, by definition T of G will be an open set in B dash. So the open sphere exists in T of G. So it is an open set. Hope you all understand, and thank you.